Hey, what's up? My name's Tyler. We're going to be talking about levitation today. So, when you think of levitation, you probably think of some crazy magic stuff like magic carpets or X-Men or something like that. But today we're going to be talking about how it's reality, how it works, and so let's get into it. It's going to be a good time. So let's look at the science behind how levitation works, so we can get a good idea of where we're going to be going. Real-world levitation relies on the physics of magnets and magnetic repulsion. So if you go back to your childhood, I'm sure you have all sorts of memories of playing with magnets. I know I do. If you did the same stuff that I did as a child, you know that if you take two magnets and stick them together, one side will pull itself toward the other magnet, and the other side is going to push itself away, try to spin and get the other side to connect. Opposite poles attract, and similar poles repel. It's all common magnet knowledge. Based on our knowledge and experience of magnets, we know that if we were able to somehow keep the magnet from flipping around, then we could keep that floating there. And that totally works for these magnets that we've used. These permanent magnets are called ferromagnets, like iron. They're able to keep their electrons all lined up in a way that is going to keep that magnetic field working, even when they aren't in a magnetic field. But the real question, which ultimately is why we're here, is how do we use magnetism to levitate something that isn't one of these ferromagnets that doesn't express a permanent magnetic field? How do we levitate something organic like us? And diamagnetics is the answer. Diamagnetism is a temporarily induced weak magnetic field experienced by all materials to different degrees which repels the magnetic field it's exposed to. To understand diamagnetics, we need to look small, all the way down to the atomic level, with all types of magnetism. The big thing is the alignment of the electrons. Here we see the nucleus of an atom with the electrons rotating around it. Within their orbits, the electrons create little tiny current loops, spin around there. These guys going all over the place, and these guys go all over the place, and so normally balance each other out, and they don't have any charge usually collectively. But when the atom or a bunch of atoms is placed in a magnetic field, we can have the electrons all line up and create a force. Albeit it's generally a small force, but that's all going to be opposing the magnetic field. When you have enough of these guys going at the same time in the same direction in a strong enough field, you can actually get some levitation happen via magnetic propulsion. The collective force from the aligned particles will be enough to lift the object in that magnetic field and defy gravity. So let's look at the math a little bit and see how this is all going to work here. Here we've got an equation for the minimum criterion for diamagnetic levitation. It's kind of a big mess, lots of weird letters here, so let's dissect it and see what we've got here. So the left side of the equation deals with the magnetic field, and the right side is going to be dealing with more of the object of interest that we're going to try to be levitating. B is going to be the strength of the magnetic field. dB over dz is the derivative of B over the derivative of the change vertically. So that's going to be the rate of change in the magnetic field, specifically the vertical axis is what we're dealing with here. On the other side, we've got mu naught. Mu naught is the magnetic constant, or the permeability of free space. That's just a constant we use to consider the amount of force applied from a certain distance by an electromagnet. Here is we've got the density of material being levitated and the gravitational constant. Both of those are pretty standard in physics, and I'm sure you have experience with that. Here in the denominator, we have chi. Chi is the magnetic susceptibility of the object, and so that's unique to every object that we have. And that's more or less just how well something is going to be magnetized, how well the electrons are going to line up against that field. Generally, for diamagnetic stuff, we usually see it in the 10 to the negative fifth range or smaller. So just looking at this equation right off the bat, we can see a few things. We can tell that our magnetic field is going to be directly opposed to the gravitational acceleration and the mass of the object, and that's going to be in the density, right? Since we are dealing with levitation, which by definition is just giving the opposite force to gravity, so when an object floats, obviously we're just going to need more force than the acceleration of gravity is going to be applied there. Okay, so let's apply our understanding now and look at an example. The coolest example I could find was an example of levitating a frog. Actually, in the 90s, there were these European scientists, I'm pretty sure they were Dutch, but they successfully levitated a frog with no negative side effects And that's pretty awesome. They set up this huge magnet and dropped a frog in the middle. There's like a hole there, and they're able to simulate 0G. The frog was just floating there. And they also levitated a few other organic objects like a hazelnut, some little flowers, even a mouse and a grasshopper. So it's pretty amazing. It actually worked here on living objects. Okay, so let's take a look at it. Here's our frog. He's a little guy, doesn't have a whole lot of mass or anything, so just like we were talking about earlier, we won't need very much force to levitate him. He also doesn't take up a whole lot of space in a small volume, which makes everything easier as well, that we don't need a lot of magnet to lift that. That's pretty awesome. Based on what we know, um, yeah, like I was just saying, we don't need an enormous magnetic field, just a big one. Since our guy is made out of water, compared to other things, as I'm sure you've noticed, water doesn't magnetize super well, and the magnetic susceptibility of water is rather small, even compared to other diamagnetic objects. So that would bring the force required for our magnetic field way up. Okay, and now let's flip this around and take a look at some problems that prevent us from being levitated. What's stopping us from levitating people? So, like we were just talking about a second ago, the bigger the object, the bigger the electric force needed to move it, more mass, more force needed. With little tiny things like frogs, there's not a lot of mass to them or a lot of volume. There isn't going to be much need for a big magnet force there. If you want to levitate something heavy or something bigger, you'd have to have a lot of force. That's just the way things work. To overcome a lot of gravitational force, you need a lot of force in the opposite direction. On top of that, with things like frogs and other living critters, or people or whatever, we need more force just because of the composition, like that water that I was talking about a second ago. The combination of these two things makes a requirement for a huge magnet. One place I was looking, another great YouTube video, if you just look up Diamagnetic Levitation, it'll pop up, I believe. That puts us at the ballpark of 45 Teslas required, which is right at about the limit of what we can make with current tech. On top of that, if you get anything that is remotely magnetic, close to that, it's going to make a big mess. And so, that's hard. Plus, a magnet that strong is generally going to be operating on a much smaller scale and like centimeter scale there. And so since we can't fit into a centimeter cube space, or 10 centimeters, sorry, cube space, we need something slightly bigger to fit a person in. And so the combination of all that means we're not going to be quite levitating humans yet, which is a bummer, but for the time being, we'll just have to let these little frogs and other little guys have a little fun. Okay, that's all I've got for today. Thanks for checking out the video, and have a good one.